Hello, I'm Chema Molina and this is Big Circuits, and today we are with Ángel de Castro, Associate Professor in Universidad Autónoma de Madrid. He was one of the experts in digital control. Here we have his book, his Control Digital basado en FPGA para convertidores conmutados, that it was his PhD thesis. But in the last year, he has been working in hardware in the loop. Hello, Ángel.
Hi there.
Can you explain us a little bit what is hardware in the loop?
Well, hardware in the loop, the basic idea is more or less simple. Is you want to test a circuit, but you don't want to test it with the final circuit. This is very clear, for instance, in power supplies, because if you are testing with the power supply and you are testing new ideas in the control or whatever, and you fail, maybe what you find is a crater in the test, okay? If it's a kilowatt or something like that. So it would be great.
Then it's a way to avoid craters.
Yes, personal damage also. So the idea is simple to explain. It's substitute something, a plant, with a digital hardware that is doing exactly the same as the original plant, in our case power supplies, would do. Okay, so it's a substitute. So it's hardware that you put in the loop. So you can close the loop with your controller, and instead of your plant, your power supply in our case, you put digital circuit.
And where do you put this loop? Which device is typical to put?
Well, hardware in the loop is not new. It started something like 20 years ago.
20 years ago?
Yes, but it started with, I think, in aircraft engines or something like that. In mechanical systems, the characteristic times and frequency are very low. Frequencies are very low compared to frequencies in electronics. So with a computer, even with a computer 20 years ago, you could emulate the hardware in real time. Okay, so it started with computers basically are offering their products with FPGAs, and using that they have made a change in something like in an order of magnitude, accelerating by 10 or something like that their previous implementations. But even that, the new frequencies for calculating each time step are around megahertz, 1 megahertz, 2 megahertz.
Of the hardware, I mean the frequency of
the frequency
working the hardware
of the hardware in the loop. So if you are using that for emulating a switching mode power supply, the switching frequency should be around 100 times slower. Okay, so
which is the maximum frequency, more or less, when you are using a microprocessor that you can emulate? Around 10 kilohertz would be possible. I mean, I know that it depends on which core, I mean, of course, but a core.
Maybe something like that, or even slower. I've seen references, about 10 microseconds, which would be that time step 100 kilohertz. So 1 kilohertz, 100 kilohertz for the clock.
1 kilohertz,
1 kilohertz for the switching frequency. Maybe reach 10, but no more than that. Okay.
And what are the companies doing in this topic? I mean, hardware in the loop. There are so many companies working on that. The companies are working using FPGAs.
Yes.
What are they offering?
The main companies are now offering HIL product, HIL, hardware in the loop products, with FPGAs. And in fact, it's their main publicity. Using FPGA, now we can go faster. opal.
How faster? Just in case, do you know more or less how
Yeah,
faster?
the numbers are, the time step can go at 2 megahertz or something like that. I think it's more or less the limit that they have achieved. Is trying to do some simple hardware in the loop, very simple, small models of a single power supply in fixed point instead of floating point,
okay.
because commercial products are using floating point, but
Fixed point in VHDL, I mean in hardware.
yes, in a hardware
okay.
description language, it can be VHDL or very long, it's the same, yes. But in fixed point, the implementation of arithmetics in fixed point is around 10 times faster than in floating point. Okay, which is the drawback? Why not to use it all the time? Because it's faster and also it uses much less resources. Also around 10 times less resources, so you can put 10 more algorithms in the same FPGA. The thing is that fixed point is hard to develop, okay? Because you have to determine the width for each signal, and you have to take much care when you are using big signals and small signals together, like in state variables. You have 400 volts in the output, and each step in the voltage can be microvolts, okay? That's easier to handle with floating point, but in fixed point you have to take care, and maybe some variables, some signals have to be large, okay?
Well, and how the companies are implementing, the companies or the people in the research in university are implementing the hardware in the loop in the FPGAs. They have several possibilities, right?
Yeah, yes. Well, first thing to say is that what you put in the FPGA, what they put in the FPGAs, is the parts that have to be run fast. Okay, so the part that you put in the FPGA has to go as fast as possible. It's to accelerate the software. And now, how to implement that? Well, the main difference in new research and what companies are doing is in the format of the signals. And format, I mean representation, floating point or fixed point.
In VHDL, all the time talking about VHDL.
Yes, well, it can be any HDL, it can be VHDL, I usually, yes, or Verilog, or there are other languages, but yes, the thing is that you are implementing hardware, so you need a hardware description language. Yes. The simpler approach is do it in floating point, because usually you don't have resolution issues.
The companies, they used to use floating point?
Yes, because the thing is that they are doing very complex models. Okay, well, very complex from our point of view. The big models, and if you have to implement a lot of models, you cannot go to the details of each one and each signal in each model. Okay, because
you need a lot of resources.
Yes, you need much more time to do the same model in fixed point than in floating point. Okay, so the advantage of floating point is clear. You develop much faster, okay, and it's easier to adapt your software, which was probably in floating point, to the FPGA in floating point, because you just adapt the language. But the thing is, okay, there is a limit in the speed. We know that using fixed point you can go around 10 times faster, more or less. Well, this can vary depending on the technology, but more or less that number. Okay,
you can go in fixed point 10 times faster than in floating point.
Yes.
You mean the hardware,
the same equations running with a clock 10 times faster.
Because
more or
again,
less.
this is due to the timing problems in the timing wave.
Yes,
no?
yes. The thing is that when you make an operation in floating point, you have to normalize before doing the operation, then you do the operation, and then you renormalize. So there are a lot of steps, okay?
And the critical
Yes,
is
yes. So that means
longer.
much longer critical path for knowing which frequency you can run, and also much more hardware, okay?
What influence do you think will have the improvements in the technology that are appearing in FPGAs? Because right now, Silence and Altera, they are improving a lot in the new series of FPGA, including even ARM cores.
Yes, a
microprocessor inside in the silicon
inside
the FPGA. What do you think? Do you think it would be a good improvement for hardware in the loop?
Yes, and in fact, as far as I know, some commercial products are already using or going to use these mixed FPGAs, which have
system on chip, right?
Yeah, system on chip with classic FPGA and also microprocessor inside the same chip, because they need both parts. I mean, what we have been doing is research, okay, and it's not a commercial product. And the thing is now, if I have to apply, do I have to develop the model, and how do I put it inside the FPGA? How I communicate? Well, the thing is communication and graphical interface and all that, and that using only hardware is very hard.
Yes.
You need a microprocessor.
An interface.
Yes. So this can be great because the microprocessor can be used for communications with a graphical interface, whatever, or maybe run some slow parts of the algorithm that do not have to run in real time or not very quickly, okay, and have the parallel hardware in the same chip. The communication are much faster, and in fact of having two chips, you have both in the same one. So
as a microprocessor to make communications, or because this is not as as powerful as a new microprocessor, but maybe for communication would be enough.
Yes, in fact, many people were implementing system on chips in FPGAs with microblaze or similar microprocessors. But the thing is now, you have a very good opportunity. Instead of having microblaze, which is is a good microprocessor, but it has nothing to do with an ARM9, which is running inside a think circuit, for instance. So
and they have two inside.
Yes, or two, or even four for future products. Yes, the thing is, it's like going from it's not a toy, but it's a small version of a microprocessor to a really powerful one that is almost the same that you have in your mobile phone. Okay, so it's now you have the computer and the FPGA in the same chip. So of course, this can be very useful for products.
Changing a little bit of the topic, now with these new devices, do you think that the digital control, that because finally at the end you are working in hardware in the loop, but also you are working in digital control to control this,
yes, that was my original topic, yes.
Then what do you think about these new devices with microprocessor inside? Do you think that will win the battle of the digital control, or also there should be...
Well, it depends on...
It should be a good fight, no?
Yes, it depends on which products. I mean, there are digital controllers that are small ones, low price. Okay, so you cannot substitute them with a think FPGA, okay? But if you were using a DSP, which was very common, DSP for making the algorithms. Okay, some complex algorithms, and you have to run them in a DSP. And then an FPGA for making the PWMs or other peripherals or whatever. Now there's a good opportunity, and instead of using 2 chips, go to a system on chip, and it will be lower price, but also very easier to develop, because sometimes the communications were the bottleneck. Okay, communicating 2 chips from 2 companies with protocols and at high speed can be very hard. So price, speed, and a single development tool, because you have all in a single one. So yes, of course, many people are moving to that.
Yeah, I know that the price is always a main topic. Even in your thesis 10 years ago, you were talking about the people is not using FPGAs in digital control because of the price.
Yes.
But also today you say that probably the price is the problem to enter these devices, these new devices. You don't think that is the same situation than 10 years ago from microprocessor DSP to entering FPGA, just an FPGA, and now from microprocessor and FPGA to system on chip that is both in together? Because the price is something that we see. I mean, we see how it's decreasing the price.
Yes. So the thing is to enter the battle while it's a novelty. Yes, because if not, at the end you're out of the market or the situation. Yes, but I suppose prices will go down, and now it's becoming much more usual to have a system on chip with both.
Of course, I suppose that there are a lot of applications that they are really low cost applications.
Yes,
where we are really far.
Yes, but there are also a lot of them in which the price of an FPGA is not a problem. So if you were using an FPGA in the past, now probably it's better for you to use a new FPGA with a microprocessor inside. Yes, of course.
Okay, then thank you very much, Ángel, and we will continue this discussion in the future, and thank you a lot.
Okay, thank you. Thank you to the
audience. Thank you, and see you in next videos.